the map symbols for a strike slope's pretty straightforward. Actually, let's put this here. Okay, so we've got a oops, do that wrong. We have a left lateral strike slope fault. So here's a map, little tree. The arrows are very, pretty easy to remember, just pointing in the direction of motion. But we use, if we're looking at a cross section, we use some other symbols, and those are what would look like the front and the end of an arrow. So the idea is like an arrow is going to have, feathers on the end, and it's going to have a point at the front. So we're looking at the tail, the feathers of the arrow. So this is going away from us, and this is going towards us. So often on a cross section, if we've got some fault, let's say this is west and east, and we're trying to indicate, that there's a strike slip fault here. You'll see symbols like that, and so this would indicate this is a left lateral strike slip fault that's cutting through this area. We're going to look at strike slip faults, some slides. These slides are available on Blackboard. So the first is just a demonstration of some little movies showing right and left lateral. So the way to think about right and left lateral is you imagine you're standing on one side of a fault. The things on the other side either move to your right or to your left. So here they're moving to your right. So this is a right lateral fault. And then here they're moving to the left. And these are the map symbols that we use to illustrate right or left lateral. So right lateral, also known as dextral, left lateral as sinistral. And this works whichever side you're standing on. So if you were standing on the far side of this one here, the person that you see there would be moving to your right. So here's a little quiz. See if you can identify the location of the fault or faults, and decide if it's left or right lateral. So maybe pause your video here. So there's actually two faults shown here. So one of them is pretty obvious. Right along here, you can see offset of these lighter layers. And if you're not sure if these really connect, there's a lot of detail. There's like this kind of red, light red, narrow zone at the base of the light layers. They get a bit darker towards the top, and then they switch back to red. So this is this spot on this side of the fault connects over here, and this is something you can see out of the window if you fly to Las Vegas sometimes. And so if you were standing here on this red stuff, it moved to the right. So this is a right lateral fault. It looks like there's actually a second fault here, and this photo also nicely illustrates this topographic expression of faults. So you can see along the fault, it's a little bit of a valley. And here's another one, and it looks to me, I'm not as sure about this one, but here's this red light red band, a lot like this one. It looks like it comes across and then jumps up to here. I'm not quite sure. It looks like some of this lighter area is compressed here. I'm not sure what's going on there exactly, but the main fault here, and possibly this one, are right lateral. So one of the signature places that strike slip or transform faults, as they're also known, are expressed is in the bottom of the ocean. So here we have the mid-ocean ridge, expressed as higher topography in reds and yellows, and then there's this linear feature that's associated with, looks like almost a gap in some places, a trench of a sort. And then you're back to a ridge again. So we know in the ridges that the spreading is occurring. So here it's, the spreading would be, this ridge would be splitting. So this side is kind of headed to the northwest, here to the southeast. This one would also be spreading. So there's motion on this fault. And again, the question is it right or left lateral? So think about that for a moment. Maybe pause your video. This illustrates what we're seeing here. So this is indeed a right lateral transform fault. You can see if you're standing here, you look across, this arrow shows how things are moving. So the faulting is occurring only on this area that's shaded with the red stars. This over here on the left, over here on the right, that's an older fault, no longer active. And then this is where the spreading, where the mid-ocean ridge basalt is coming up. So all faults are going to end at their, they're going to have ends. And so one thing that happens on a strike slip fault, if you have a nice right lateral strike slip fault here, and we're looking at a map symbols again, these are normal faults, normal fault symbols. So you're pulling this material away from the material over here. So that sort of opens up a space, and that's normal faulting will occur in that area. And you also have a decrease in the topography, at least a lowering of the average elevation. Likewise, here we have another right lateral fault, but it's arranged the way that it kind of curves so that there's a compression in this area. This part is coming closer to that part, and that's accommodated by thrust faults. This is the map view. And then looking at a little block diagram here of this end, you can see these nice duplexes and thrusts, solving what we call the space problem. So this is one way that, it's not always obvious if it's a right or left lateral fault, but if we see a curve in the fault, and we see that it's associated with thrusting or normal faulting, that's one way of telling the sense of motion, which is one of the most basic things that we're looking for or interested in on faults. Is Los Angeles moving north or south along the San Andreas Fault? So take a moment to remember, or to just kind of draw these out, this strike slip fault with a curve, and see if you can be clear about whether it will be a thrust fault area or a normal fault area, depending on how it's curving. And these curves and strike slip faults occur not just at their ends, but in their middles. So this shows what's called as a releasing bend. So this area is getting bigger. It's opening up space. So this is we call this a releasing bend. And normal faults will occur here. Topographic depressions, ponds, basins, and likewise, if it is bending in a way that's causing things to be pushed together, you get thickening of the crust, faulting mountain ranges. It's called a restraining bend. And this shows a nice sag pond in a releasing bend on a major fault in Iceland. So these so-called sag ponds can be quite large. So there's many famous transform faults. San Andreas Fault is one, probably the most famous. Alpine Fault in New Zealand, Altan Fault in the Himalayas, North Anatolian Fault in Turkey, and the Dead Sea Transform. And we'll look at examples. We'll look at some images and discuss these next. So here's a sort of oblique view of part of central California. So San Francisco is up here, and the San Andreas Fault is running northwest, southeast through here. And you can see in 3D how they've sort of showed these different blocks. So the San Andreas, it's actually part of is often associated with a system of other faults, some of which are older and less active. All of the faults here have the same sense of offset. So think about this for a second, if it's right or left lateral. It's a right lateral fault. Turkey has a beautiful fault, the North Anatolian Fault. So as Arabia is pushing north into Eurasia, it's kind of squeezing out Turkey to the west. These little arrows are motion that's detected from GPS. So people put out GPS, leave them out for months or years, and they can see the motion recorded in those. You can see this kind of a rotational motion, and what that means is that this stuff you can sort of think of it as a watermelon seed being sort of squeezed out to the left here, and so that causes a major strike slip fault here, right lateral strike slip fault, and there's been a series of earthquakes along this fault in recent years, and Istanbul there is kind of due for a major earthquake. Here's another view of that. You can see, so as this is being pushed out to the west, there's some subduction zones here as well. So teeth are on the hanging wall, so they're accommodating this motion as well. So the stuff being pushed, and then the Mediterranean Sea going underneath. This is another strike slip fault, left lateral strike slip fault here, associated with the same system, the Arabian Fault moving north. So the Dead Sea is along here. Here's another view of that. So you can see, as with this left lateral fault, Dead Sea Fault, as it bends like this, it's gonna be opening up a gap here. And that's where the Dead Sea is located. You can see how the rifting here, opening up, spreading, is pushing the Arabian Plate north, and how this area of Turkey is moving to the west to get out of the way. This area as well, kind of moving a bit to the right. Here's a satellite view of that Dead Sea Transform Fault. You can see the fault moving along here. There's the Dead Sea. This view here showing the topography, shaded relief map. Again, this fault really stands out in the topography. I think you can see the North Anatolian Fault as well. So New Zealand is also located on a plate boundary, and they have a fault, the Alpine Fault, which goes for around 800 kilometers. Two different views here. There's subduction zones on either end. It's a rather complicated system, but in in the South Island of New Zealand, the Alpine fault is this very straight feature. It splits into several strands here, sort of like what we saw earlier in San Francisco area. And then you have these volcanic arcs. Here's an aerial view from the southern Alpine fault, and you can see it really stands out in topography. It seems to be affecting the vegetation cutting through here. And the amount of the scale's not really showing up here very well, but these rocks here connect. The same rocks are found up here. So there's some really distinct rock units that sort of bend in here, and they bend in a way that looks as if they've been dragged along the fault. So this is another right lateral fault, and then you find them again up here. So there's quite several hundred miles, 400 kilometers of offset. Here's another satellite view of the South Island. You can see the fault running right along here, separating the higher mountains that have snow on them in this view. And that's partly because the Alpine fault is an oblique fault. So this stuff on the southern side of it, it's not only moving along strike, but it's pushing into it, and it's being pushed up right along there, forming this mountain range, the Southern Alps. So the Alpine fault is definitely an oblique motion fault, unlike some of the other ones we just looked at.